friends, welcome back. So in our previous lecture we discussed about weight estimation, where the total weight of this aircraft is summed up as the structural weight, as a propulsion weight, right. Total weight is summed up with structural weight, propulsion weight and payload, as well as weight due to fuel. So we express this total weight or takeoff weight as a weight fractions, structural weight fraction plus propulsion weight fraction payload plus fuel weight fraction. Right. So where W takeoff is obtained with the help of, so W takeoff is obtained by rearranging this equation, where in the denominator you have all the weight fractions, and we also witnessed WF by W takeoff is equals to 1 minus W6 by W1, where W6 by W1 is equals to W5 W2 by W1 W3 by W2 W2 W4 by W3 W5 by W4 into W6 by W5, right. So these are the weight fractions, weight ratios for various segments, right. So say typically we have segmented the entire mission as takeoff, climb, cruise, approach and landing. So we have segmented this entire mission based upon the dynamics during that particular phase, right. So this weight fractions represents the fuel weight that is consumed during these phases of this mission, right. Now out of which we also discussed that these are like more or less, for takeoff, climb, approach and landing we have weight fractions from the historical database. So what that differs from UAV to UAV or the aircraft to aircraft is the cruise profile or the cruise fuel consumption, which mainly depends upon the mission requirements, right, or the tasks to perform. Now, so in order to calculate this cruise performance, we studied about range and endurance, right. We started with range and endurance, but we finished what is range. We have defined specific fuel consumption of this IC engine based systems, which is the amount of fuel consumed to produce unit power, right. So the power that we have discussed is the shaft. So this will be the shaft power. So Cp, since it's a Wf is negative, so Cp is a figure of merit. So we'll define Cp as minus Wf by Psh, right, shaft power. And we witnessed that the range or the range for this propeller driven UAV is given by eta propeller by Cp into L by D into ln of Wi by Wi per I plus. So if you want to know the weight fraction, fuel weight fraction, then what you have is Wi plus 1 by W is equals to e raised to the power of minus R into Cp divided by eta of the propeller into L by D. This is the same equation what we discussed in our previous lecture. Right. Now let us discuss about fuel weight fraction for loitering. Loiter. So what is the specific fuel consumption? By definition, Cp is minus W dot F by Psh, right? This is equals to minus eta of the propeller into W dot F divided by T into V infinity, right? This implies Cp is equals to minus eta of the propeller divided by T into V infinity into dWf. We know that, right? So dW is equals to dWf. Since dW is equals to dWf, you can write eta into dW. dW by dt. So dt is equals to minus eta of the propeller into Cp into 1 by V infinity into W by T into dW by dt. Sorry, into dW by W. So this implies, so in order to get the endurance, I have to integrate it over the time 0 to T, right? So the endurance or the time of flight is equals to minus integral over Wi to Wi plus 1 into eta of propeller by Cp into 1 by V infinity into L by D into dW by, right. So endurance is equals to, there are two ways to integrate this. One, like constant velocity and constant CL climb, CL cruise. Like both the lift coefficient and velocity remains constant, but as the fuel is consumed, since you are having same lift and same velocity, we know L is equals to W, right, in cruise, which is W is half rho V square S into CL, right. So one such condition in which cruise can be attained is constant CL and constant V, right. And in that case, this W is continuously changing because the fuel is getting consumed, right. The only variable that has to change is density. That means you will end up gaining altitude, which is known as cruise climb, right. Just like a balloon, you don't actually climb, but you keep gaining the altitude because there is a additional lift acting on the system, which is greater than the weight, right. Why? Because there is fuel consumption. We call it as cruise climb. So if we consider, say, assuming that density variation in the density is allowed, right, and say V and CL is constant, so this particular terms remains constant. So in that case, what will be this equation? So there are two cases, right. Let us solve this for this particular case where density is allowed to change. That means the aircraft can gain altitude as it cruises, right. So in that case, for constant CL and V infinity. So for that case, what happens? The endurance is equals to minus or eta of the propeller divided by Cp, and velocity remains same, constant, 1 by V infinity into L by D remains constant, because CL remains constant here, CL and C, when CL remains constant, CD will also remain constant here. So the integral will be ln of W of I plus 1 or Wi by W plus 1. So this is the endurance of a UAV, of a propeller driven UAV, when you have constant velocity and CL, right. And for constant density and CL, that means you don't want to vary the altitude, you want to have your cruise at a particular altitude and then the CL is remain constant, which means the pilot has to continuously decrease the velocity as the fuel load is decreasing. It's more a quasi study, right. So what happens in that case? What will be the endurance? Is equals to integral over, so this is the equation of endurance in general. So say W estimation 11, so endurance is Wi plus 1, or say Wi plus 1 eta of propeller C of P into 1 by V infinity CL by CD into dW by W. Now, since we are talking about cruise condition, we know L is equals to W. So for this, lift is equals to weight, which in this case the corresponding velocity of flight is twice the wing loading divided by rho into CL. Substitute that here. So what you have is integral Wi plus 1 to W I eta of the propeller by Cp into square root over rho s by 2 into CL power 3 by 2 by CD right, CL power 3 by 2 by CD 3 by 2 by CD and dW by W into W power 3 by 2, right, because there is root over W here and 1 by root CL. So it becomes CL into CL power CL plus CL into CL power 1 by 2, which is CL power 3 by 2 by CD, and W into W multiplied by W raised to the power of 1 by 2, which is W power 3 by 2. Okay. Now here we have density is constant, we assume density is constant in this case and CL is constant, right. Rho is constant and CL is constant. If you say CL is constant, CD also remains constant. So other than this particular term, everything else is constant in this case. So what you have here, so the endurance for this case is equals to eta of the propeller by Cp into CL power 3 by 2 by CD into under root rho s divided by 2 into minus 2 1 by root over w from wi to wi plus 1, right. So this will turn out to be the ratio of propeller efficiency to Cp, specific fuel consumption, into root over 2 rho s, density at that particular altitude, into Cl power 3 by 2 by Cd, into 1 by root over Wi plus 1 minus 1 by root Wi, right. This is our equation. WE 13. Weight estimation 13, right. So Wi plus 1 is smaller than Wi, so this quantity is larger than this quantity, right. So this is a positive value, so everything else is positive here, right. Now from here we generally consider for initial weight estimation, that's why we get an estimate out of it with the assumptions, right. We are having certain assumptions here. With that assumptions we will get an estimate of the fuel load, so which may be off by at least 20% of the actual value, right. So to start with, we can go ahead with these assumptions and say, if you want to find out Wi by Wi plus 1, all you have to do is multiply the given endurance by Cp and V infinity. V infinity is the corresponding velocity of flight, and you should know what is the corresponding L by D, right, and propeller efficiency as well, right. Once you know this, then you will be able to find out what is the weight fraction. So we will do a small example once we discuss this weight estimation as well as wing sizing, right. So when this endurance can be maximum, in this case you have to fly at L by D maximum. So the corresponding velocity for L by D max is V for L by D max, right. You should fly at the corresponding velocity where L by D is maximum, right. In this case, when E can be maximum, when Cl power 3 by 2 by Cd has to be maximum here, right. You fly at sea level, this particular term will be higher, right. Assuming these parameters are not going to be affected with either velocity or altitude, right. And you have, if you want this E to be maximum, rho has to be at sea level, and Cl power 3 by 2 by Cd has to be maximum, and you should carry more fuel, right. This difference has to be more, okay. That means there should be a lot of reduction in weight, right. When there is a lot of reduction in weight, this quantity will be higher compared to this, so the difference will be higher there, where you will end up having high endurance. So for this case, so E max can be attained at L by D max and V for L by D max. So what is L by D max? 1 by root over 4k CD naught, where Cl is equals to root over CD naught by k. And the corresponding velocity you can find out. Similarly, for this case, Cl should be root over 3 CD naught by k for E max. In this case, corresponds to Cl for Cl power 3 by 2 by CD max, and CD is equals to 4 CD naught. So the induced drag is 3 times the profile drag in this case. Induced drag coefficient is thrice the profile drag coefficient. right? Okay, till now we are talking about fuel based system, right? So in the previous lecture we were not able to show you a proper engine, right, proper IC engine. So this is a bigger version of it. So I have the specifications of this as well. So it is GF40 OS engine, right, and it has a 39.96 cc and for displacement and a bore of 40 diameter bore and a stroke length of 32 approximately, and the feasible RPM is about from 1800 to 9000, right, and the output from this is 3.5 HP at 8600 RPM. So it weighs about say 1.7 kgs approximately. So you can see this is an spark plug. There is a igniter for it, right? You can connect it here, and this will be connected to this particular wire, which actually generates power with the crank rotation, right? This particular valve that you can see here, see, it will automatically come back to 0. You can control the fuel air mixture, right? This is like a lid for this fuel air mixture, right? It acts like a lid to this mouth, and you can see there is a valve that will be rotating as I rotate this lever, right? So it actually controls the fuel air mixture and so the RPM of this shaft, right? So once you mount the propeller here, you will be able to convert this shaft power, available mechanical shaft power, to the useful power, right? So I thought of showing you some like brushless motors as well. So this is it's a carbon fiber propeller, 3 carbon fiber propellers, 3 blades mounted on this hub, right, which is attached to the outrunner. It's a 515 kV outrunner, and this hub is a foldable hub for these propellers. There is a JetCat jet engine. You can see this. It's a small jet engine, mini jet engine, which can produce a 220 newtons force, which is approximately 22 kgs force, right? It can produce a 22 kg thrust. So if you can see a stator there in the front. It weighs about 1.8 kgs, and some of the specifications I have here. Maximum thrust is about 220 newtons at 1,17,000 RPM. So this RPM has a range of 35,000 to 1,17,000 RPM. So it weighs about 1.8 kgs and ideal thrust of 9 newtons, which is approximately 1 kg of thrust, right? So 30 centimeters and diameter of 11 centimeters, right? Okay. So this is the jet engine. So if time permits, I will try to install this jet engine in a delta wing configuration and we'll fly. Otherwise, we'll fly 1 or 2 delta wings with normal propeller driven propeller driven engines which are powered by battery. Okay. So let us talk about how to estimate the battery weight. Say if you are going for a brushless motor similar to this. So if you want to power this brushless motor, you need to carry a battery. Say if you install this motor on a UAV, right? So you need to know how much battery I need to carry. Say if I want to have a certain mission requirements. Say if 10 kilometers range, or say if I want to have an endurance of 1 hour, so how the battery weight changes, right, as the mission requirement changes. So let us look at how to estimate the battery weight, right? For an electric powered propulsion system or a battery powered propulsion system, what we need to define is specific energy density, no, specific energy density of the battery, which talks about the amount of energy stored per unit weight of this battery, which is watt hour per kg. The units of this specific energy density are watt hour per kg. So each and every battery that we use to power these motors, they have certain energy density, right? So based upon the available energy density, you will be able to estimate the battery weight once you know what is the corresponding energy that is required to perform the particular mission, right? Okay. So let's go back to this equation. So weight, overall takeoff weight is equals to structural weight ratio times the takeoff weight and propulsion weight ratio times the takeoff weight plus payload plus battery. Right. So it's a bit different compared to that of fuel based system. Okay. So what we go ahead with this is, so for this particular mission required, how to solve, how do we estimate the battery weight and the overall takeoff weight. So similar to that of earlier case, we consider this structural weight ratio and the propulsion weight ratio from the historical database, right? And we also consider what is the overall takeoff weight here. How? We take the nearby flight vehicle which is performing a similar mission, right? So we will take the weight initially from the historical database, even the overall takeoff weight. At the same time, we will take the structural weight and the propulsion weight, right? And the payload is given for you, right? So let us say these things are known for the time being. So it's an iterative process, but in this we will try to address, say, if this is the overall takeoff weight, what is the percentage of battery weight for that overall takeoff weight. Let us say if you want to build a UAV of 5 kg, now you should know what should be the fraction of this overall weight of 5 kg should be the battery weight, right? So let us solve that problem first, and then we will see how this iterative process works to actually find the weight estimation, right? Weight estimation of the new design. Okay. So how to go ahead with this? Say we know specific energy density, say this is known, specific energy density is known. You need to know what is the energy so that you will get to know what is the weight, right? That means weight of battery is equals to energy required or energy to be supplied to the system divided by SF specific energy, SED, specific energy density, right? So energy required, energy is watt hour or joules, right? Watt second in fact, or watt hour per kg. Okay. So this is energy required is watt hour and this is watt hour per kg. So what you're going to get is a weight of the battery in kg, right? And now how to find out the energy required? So for any mission profile, say, so again going back to this mission profile, typical mission profile, where it involves takeoff, cruise, climb, cruise, approach, descend or glide, landing. So the total energy required is equals to, ET is the total energy required, is equals to energy for takeoff plus energy plus climb. It's a summation of energy for this entire phase, right? Energy for climb plus energy for cruise plus energy for descent and energy for land. So if you see here, so most of the UAVs, the major part of energy is consumed during cruise, and to some extent, very little extent can be climbed. So say if you know the cruise energy, and descent is most likely a glide in case of UAVs, unlike commercial aircrafts, the descent is most likely a glide here, and landing, of course, it hardly requires energy. So say if I estimate the cruise energy and also the climb energy required, then I will take some factor of safety as to account for this descent, landing and takeoff. So this is my initial estimate, right? Now how should I find this cruise energy? So one way to do that is energy for cruise is equals to power required during cruise into total time of flight. If I know the total time of flight during cruise, I will know what is the corresponding and if I can estimate the power required during cruise, I will be able to estimate the corresponding energy required during this cruise. So how should I calculate this power required during cruise? So power required is drag into velocity, right? Of course, this energy required during cruise, you need to have a factor of safety, right, to account it for the other cases. At the same time, the efficiency factors, right? You can multiply all the efficiency factors, that's pi into eta, whatever the final or required is equals to pi into eta into, so say pi into eta into energy cruise, right, where pi I is equals to 1 to n eta I, right. So where eta talks about factor of safety, efficiency and all these things. So you multiply all those and find out what is the corresponding energy required. You should divide this, in fact, right, because this is the output that you, this is the input that you have to give, right. From the battery you need to supply this much of energy. So this is like inverse of it, right. So if you do this, then you will be able to estimate what is the actual energy required. So this may also include the, what do you call, battery cannot discharge 100%, right. There is a limit for discharge. So that limit can also be included, as well as there can be losses when you connect this battery to a particular power plant, right. Those losses can also be included here, right. Now let's go back to this for energy for cruise. So this is drag into velocity to delta t. What is drag? Half rho V infinity cube S into CD into delta t, right. So velocity for this particular cruise mission will be given, and you will be asked like how much time, I mean as a part of mission requirements you will get this delta t. You need to know what is this CD in order to figure out what is the cruise energy for cruise, right. This is like, no, instead of, there are two ways, right. So you are actually given the information about areas, reference area and CD. Let us say if you don't know this reference area and CD, what happens, right. What I can do, so energy for cruise is equals to power required into delta t, where power required is drag into velocity into delta t, right. Or power required is thrust required into delta t into V infinity. So what is thrust required? So thrust required is W by L by D. So if you can refer our previous lectures, you will be able to find, because T is equals to D and L is equals to W for cruise, right. So thrust required is W by L by D. Now if you substitute that in that energy required equation, this is like W by L by D into V infinity into delta T. So all you need to know is what should be the L by D of flight. So usually it will range from 10 to 15, right. for a normal UAV. So V infinity will be given, you know, you have initially considered some W takeoff, which is that same W here, right? You can, this is takeoff into V infinity into delta T, right? Now you know what is the energy required here. Now the weight of battery is equals to, or this is energy for cruise, sorry, energy for cruise. So energy required is equals to energy for cruise divided by efficiencies, eta I, whatever the efficiencies that you want to consider here. So this is our WE. What's the number? 14. WE 14 and WE 15. So say if the cruise is at a constant velocity, then if you want to have maximum cruise or minimum energy, and you have to, so for the same time of flight, if you at the same velocity, or say for the same time of flight, if you want to spend minimum energy, all you need to do is to fly at maximum L by D, where the corresponding V infinity will be, right? You have to fly at the corresponding V infinity as well. V infinity at L by D max, right? So weight of battery is equals to energy required by SCD. Energy required, we got it from the ER, which is E cruise. So this is for initial estimate, right? Phi I is equals to 1 to N eta I, right, into specific energy density. So this is the weight of the battery, and the percentage, the ratio of the what do you call, battery fraction divided by total takeoff weight. Then you will get to know, say if you want to build a 5 kg UAV, how much energy density, how much battery you need to carry, right? So let's solve a small example. So we have slowly started the design of UAV, right? Because we initially figured out how to select a power plant or the engine sizing, and then we are trying to figure out how to estimate the total weight, right? So let's take one small example. We'll also come back to the iterative process once we solve this example, right? Example here, following are the specifications of an all-electric propeller driven wing alone crop delta UAV. So what is given is weight is 3.5 kg, span 1.5 meters, CR root chord 0.9 meters, and tip chord 0.15 meters. And also the plots of CL versus alpha of this entire UAV, full scale UAV were given here, and there is a plot that represents CL square versus CD for this full scale UAV is also given. And then coming back to the question, find the battery weight fraction of UAV to carry out a 20-minute loiter with a trim angle of attack 4 degrees. What should be the additional battery weight required to perform the same task at 3 km altitude? Right. So, first let us solve this question in first place. Also assume energy density of the battery is 0.15. Assume a specific energy density of battery is 0.1 watt or kilowatt hour per kg. Also find the osmosis efficiency factor E. So, see, I am using, if you observe, I am using the same configuration in most of the examples. So, it is worth you get used to these numbers, at least the aspect ratio, weight and all these things, so that it will be helpful for you during the end semester examination, right. So, you can refer our previous lecture. So, for this configuration the weight is given as 3.5 into 9.81, which is 34.33 kgs approximately, newtons, right. It is given. So, S is again V into lambda CR by 2 into 1 plus lambda, which is equals to 0.787 meter square, and then lambda is CT by CR is 1.167, 0.167, and AR is B square by S, which is equals to 2.87. Right? It's a crop delta wing UAV. And now, what we need to do here? We need to find the battery weight fraction of this UAV to carry out a 20-minute loiter at a trim angle of attack of 4 degrees. SED is given as 0.1 kilowatt hour per kg, right. So, SED is 0.1 kilowatt hour per kg, which is equals to 100 watt hour per kg, right. So, let us figure out what is a battery weight that we need to carry in order to complete this task for this particular UAV. So, in order to find the battery weight, what I need is the energy required for this system, right. How do you find energy required here? So, energy required is equals to, assuming it is 100% efficient in all the cases in this case, right. I mean, at all the, I mean, say there are various losses that happens, right. So, assuming there is no loss throughout the process, right. So, energy required is equals to drag into velocity is a power required into delta T, right. So, why we consider drag here? Because we can also consider the other case, like what is the L by D for this particular configuration, or say if you know what is the CD here, since you know at alpha is equal to 4 degrees, you will know the corresponding CL here. At alpha is equals to 4, the corresponding CL is 0.2 approximately, right? And from here you'll be able to find out, see, this is CD versus CL square, right? Which means in the linear regime, this is like y is equals to mx plus c, it's a straight line, right? Where y is CD is equals to CD naught plus slope here will be k into CL square. So this straight line will give you the drag polar when you plot CD versus CL square, right? Those CD naught you can find out and k you can find out. So for this particular case it's 0.035 and k value is 0.16 into CL square, right? Once you know k is equals to 1 by pi e AR, you know the aspect ratio, you can find out the corresponding Oswald's efficiency factor, which is approximately 65%, right? You can calculate that here. So ER is equals to drag into velocity into the time of flight. Here it is 20 minutes of flight. Now what is drag here? Half rho v square into v infinity is v cube s into CD naught plus k into CL square into delta t. So at alpha is equals to 4 degrees, you will be able to find out what is the corresponding CD, because you know CL and you know the CL square value, you can find out the CD, or you can simply from this you can substitute in this equation once you have this, right? From this 4 degrees you know what is the CL value, you can substitute this. So 0.5 into 1.225 into 20. What is the velocity of flight here then? We know L is equals to W. For the level flight condition we have L is equals to W. So the corresponding velocity is square root over 2W by S divided by rho into CL, corresponding CL. CL at alpha is equals to 4 degrees, right? So what is the value here? It's 18.1 meters per second approximately. 18.87 meters per second. Meter per second. Now substitute that velocity here, 18.87 cube into 0.787. What is CD naught plus KCL square? Or the corresponding value here, you can figure it out, which is approximately 0.04. Yeah, CD value is 0.0414. So this is CD is 0.787 and the total time of flight into 20 into 60, because it's in minutes, right? So 20 into 60 is like 1200 seconds, right? So the total energy required is approximately 160,800 watt second. 160,800 watt second. So if you convert that to, so let's convert that to watt hour. Energy required 160,800 divided by 60 into 60. This becomes 44.66 watt hour, right? Now you know energy required in watt hour, you know SCD, that is 0.1 kilowatt hour, which is 100 watt hour per kg. Now divide this, so the total battery weight should be equal to energy required by SCD, which is 44.66 watt hour by 100 watt hour per kg, which is 4.446 kg, right, which is approximately 440 or 450 grams. So for this 3.5 kgs UAV, so half a kg is a battery weight. You need to consider half a kg as a battery weight for this UAV.